So again, if you were not here yesterday and you want to participate in Module 7, you need to create a Terra account, and then with your Terra ID, which is the email login that you used, you have to complete Google Doc form to be able to participate in Module 7. The information and the instructions are posted in Slack, and then there was also an email sent. I think it came from Stephen Mosher from Johns Hopkins. You want to check that. If you missed that email, again, go to Slack and then check that information and then complete it. Also, you cannot do data science without ethics. So next week for the Module 8 seminar presentation, there will be a talk on ethical data science that will be talking about the ethics of data science. So that will be next week, Thursday at 11 o'clock. And then also don't forget to complete the evaluation that will be posted in Slack, and then also it will be posted in the chat area here. So Dr. Washington is here. Yesterday, she gave a very informative presentation on neural network, and then she is going to continue with that. So welcome again, Dr. Washington, and then it's all yours.
Hello, everyone. Good morning. Hope you are having a good Friday morning. So today we are going to continue on in our discussion about machine learning using neural networks. Okay. So as mentioned, today is part 2, and then once again, I'm Gloria Washington. So what I wanted to start out today with was some key takeaways from part 1. Some key takeaways from part 1 that I think that I wanted to make sure that I didn't leave anyone confused or anything like that was to start about talking about some of the things that you need to do. When we were working on the hands-on part, I got a lot of different questions about this area that we call data pre-processing. And then there were also some questions between what's the difference between data classification and regression. And specifically in the section within the hands-on part, there's a part that talks about regularization. And rather than go into that yesterday, I felt it was really good to start off addressing it today. So it fits underneath overfitting, and then we'll talk about this idea of regularization. Okay, so it isn't an assumption as a data scientist or even computer scientist, anything when you're trying to work in this area, that data pre-processing is step 0. And you'll see a lot of different courses where they devote at least 4 weeks to this like lengthy process of data pre-processing. I'm pretty sure some of you have already addressed this or know a little bit about data pre-processing. So for those of you who already know about it, just listen to me and but tune me out a little bit. Anyway, so there are 4 different areas for the most part of data pre-processing, and it involves many steps. But the first one that before you even think about using your data, you must clean it. And so in the example that we got, we had data that, of course, is sanitized, and it's perfect for, for this kind of class. But I don't want you to think that you're just going to get a comma separated file and just be able to use it. In some cases you can, unless you know a researcher who has already done some things to it. But most times you're going to need to clean it. And then there's also this thing called data munching. Data munging is also referred to as data wrangling. Talk about that only a little bit. Data normalization was a section that was also in the hands-on exercise. We'll talk about that, and then why it is important for dividing your training, test, and validation sets. These are all the steps that kind of occur at step 0 before you jump into creating your first neural network. So what is data munging? As mentioned, data munging is also called in some contexts data wrangling, but basically it's looking through your data set to figure out, well, this data has some categorical information, it has some, numerical information. So when you're looking through the data set, you're going to have to figure out how do you deal with missing or negative values. Specifically, how do you deal with specific elements within the data set that you know for a fact should not be negative. So those missing values or negative numbers or things like that is called data cleaning. And then the next step, you filter the data, you sort the data, you merge and concatenate it together with other data sets maybe that you already have, and then you save this for the future so that you're able to utilize it in your machine learning algorithms. I'm not within the steps or within this actual presentation today going to show how to do that, but there are several different online resources for you guys to kind of look at. The one that I like the best, that I steer my data science students to and computer science in the class that I teach, is DataCamp. DataCamp has all these cheat sheets that allow you to, they're PDFs. You can also just, bookmark them as a HTML site, as a web page as well. But anyway, the three main things, at least that I found that we used in my class the most, had to do with one, opening and reading in your comma separated file, sorting. So a lot of times, as mentioned, the data sets need to be sorted and so that you can look through them to understand and figure out if there are missing values. And then there are summary information, which are gives you information about the mean, the min, and any specifically descriptive statistics that kind of go into the data set. And then there is a drop command. And sometimes you're going to have comma separated files that are Excel sheets. So Python is really good. It gives you commands to actually convert your comma separated files to Excel, or to actually read in separately an Excel sheet so that it's useful. So as mentioned, these slides are available, but these are links that take you to the DataCamp cheat sheets, but I've also added them as at the end of this presentation in the appendix, because there's not enough time, of course, to go into doing it on your own, but like when you have time, look at the cheat sheets and go to DataCamp and see if they have some other ones that are relevant to the work and research that you guys may do on a daily basis. Okay, so moving right along from there, there is data normalization. So data normalization, the section that we had in the hands-on part, one of the questions was, well, what is it and why? A lot of you may already know this. However, the question was like, what is it and why did we have to do that in that step? That was a really great question, and I wanted to make sure I touched on it. So sometimes you obtain data from various sources. In the examples that you were given yesterday, you got a comma separated file. But as mentioned, there's going to be times where you're going to obtain, especially in your research, several comma separated files. And a lot of times these data sets are in different ranges and different scales. So a really quick example, when we think of like the testing example that I gave in the simple example, where you have quiz scores that are on a scale from 1 to 20, and then you have homework scores that can be from 1 to 75, or you have exam scores that are between 1 to 100. So trying to merge and utilize this information together. Think about if these were 3 different tables or 3 different data sets together, you would need to make sure that they're on the same scale. So normalization is a technique that often is applied before data science in the data preparation stage. And basically it's just changing. Usually the common method is to change everything to be between 0 and 1. But the goal of normalization is to change the values of numeric columns in the data set to this common scale so that larger numbers or even outliers don't distort the differences in the ranges of values. And remember, if you have larger numbers that have not been normalized or converted, it can skew toward weighting those actual numbers higher. So I just say that to say, normalization is something that you really can't get past. So there are several different techniques. The techniques that was utilized in our particular module was the sigmoid normalization, and where it normalized all the values between 0 and 1. This is common. There also is Z normalization, where it's a standardization of all of the values. There's the min-max, where you just put everything using the min and max of each individual particular variable. And then there is unit vector normalization. I won't go into all of these. However, I have provided a link at the bottom so you can find more information about each individual technique. But the technique that we utilized yesterday was sigmoid normalization, which turns everything in between 0 to 1. Okay, so how do I prepare data for machine learning? So this gets into the training set, test set, and validation set. And it is very important when you are doing this pre-processing before you even start to do machine learning or anything related with neural networks, that you must divide your data into a training set, a test set, and a validation set. So the training set provides example data that we want to train or get our model to learn from. It's like, it's like showing a child many different examples of certain things so that they can recognize them in the future. The training set is a subset of the original data that we were given. You want to usually train on as much data in the training set as possible, or in the data set that you've been given as possible. So there are some common ways to pick the training, validation, and test sets. So there's this thing called cross-validation. I won't go into what that truly is, but within this link I provided, if you go to this link, there's also more information about the many different techniques. But cross-validation just says, within my actual input data set, that is assumed to be one data set, right? One comma separated file. However, there will be cases where you may have 2 comma separated files, or you may have 3, but leave one out. Cross-validation is saying that you have one. This has occurred a lot, at least I've seen it a lot in biometrics, where you train on everything else but one, and then that one you actually test on. That has been used a lot in computer vision, and then also biometrics. And there is K-fold, where you can actually pick the K that you want to actually leave out for the test set and the validation set. So, and then there's 80-20, where you train on 80% of the data that is included in your data set, and then 20% you test on it. And within that 20%, you would further divide it into a validation set as well. So basically, these techniques just allow you a way to automatically come up with a training set, a validation set, and a test set. But These techniques have been utilized across the board in machine learning to actually help you pick the training set, validation set. And I think the actual example that's shown yesterday was like 30% was used for training. And then there was another example where 20% was used for training. But a test set is important because this is a subset of your data that's used to validate your model, and it's used so that you can get performance information of how the model will perform. And then within that test set, you may have a validation set. The validation set is just so you can see if you have overfitted. And the validation set should contain data that has never been seen before. This is important because, as mentioned previously, the model can learn from the input data that you give it. And depending on how long you let it train for on that data set, you can have this thing called overfitting. We talked about it a little bit yesterday, but not in depth. I wanted to make sure that I'm not going really fast and answering questions. So do we have any questions from the stuff that I've already covered? Okay. Okay. So there was also a discussion yesterday of what is the difference between regression and classification, and how certain elements of the neural network can, kind of mimic themselves to regression. So classification is when there are a few distinct outputs called classes and that the input could be mapped to. And classification also assumes that usually there is one single correct label for each input. And regression is different. It predicts a real value quantity rather than a class. So an example of that is, suppose we want to predict teacher ratings on a scale from 1 to 5 from student evaluation. So at Howard University, students rate professors using an IDEA survey or whatever they use nowadays. And usually these ratings, I think 1 or was like not helpful or whatever. And then you have 5 all the way to the person was really helpful. So in the case of regression would output a real quantity. And let's say for this particular example, the real quantity would be 3.25. Classification, on the other hand, would predict which distinct class. So let's say it would predict a rating of a 3. The neural network example provided that we went through yesterday would be an example of classification, not regression, because it does not predict a real quantity. It predicts a class. So what happens in what we saw yesterday is an accuracy score is output for each epoch. And the accuracy score is how well our neural network was at predicting the correct label or the correct class label in the validation and test sets. Are there any questions with regard to this slide?
Can you again say about the validation and test set?
Yes.
The difference between, because you mentioned train set, then okay, the validation set and the test set. There's a 3 kind of data set.
Yes. Okay. So when you are picking, so the true difference between the training set, the validation set, and the test set is the training set is what you are using initially to tell your machine learning model, these are examples of the classes or the class that I actually want to predict. That the training set is used entirely for that. The test set, on the other hand, is used to test how well your model learned all that information from the training set. The validation set also is used to do that as well. However, most people use the validation set as a way to introduce new data to this model and determine if your model has actually been overfitted. And overfitted means that it's learned everything that it possibly can from the training set. It's learned every nuance of it, even the noisy data. And that's not really good as far as from a neural network standpoint. It's bad because when you introduce new data to it that it's never seen before, which is usually contained in the validation set, it usually does not perform as well. So the difference between test and validation, they're both used to look at the performance of the model. However, the validation set, for the most part, should be never before seen data. Of course, that is available in the test set as well, but it also helps you to understand if your data has been overfitted.
So, like a training, and that is coming from the same data set, right? Validation data set maybe is a new data set, right? Training and the test data set. No?
Well, some people, it depends on the scheme, right? So for the example that you saw yesterday, the validation set was just a subset that was taken from the test set. So it was like they allocated a specific amount of randomly picked items. I think it was 30%. So what they did was take 30% of that original data set, and then from there it was subdivided into a validation set, right? Some schemes will say, okay, I have this test set that I have, and I have found new data from elsewhere and have it be a validation set. For purposes of the example that you saw yesterday, the validation set was actually derived from the test set. Does that make sense that I'd answer the question? Was that was a yes?
Mm-hmm.
Okay.
Yes, good. Go ahead. Thank you.
Mm-hmm. Okay. Okay. Yeah, so going back to this, as mentioned, the accuracy score is how well our neural network was at predicting the correct label in the validation and test sets. You actually want to have a model that performs the best on the validation set, because remember, the assumption is that the validation set contains data that the model has never seen before. And it should, if it performs well on data that it has never seen before, and that is an example, of course, of the training that it has been trained off of, but it performs well on data that has never been seen before, then you want to pick that model. And so we get into what was overfitting and regularization. And within the example yesterday, overfitting was mentioned, and then also regularization was mentioned as well. Overfitting happens in a complex model. So as mentioned, the examples that I showed you is that with neural networks, people for the most part, they don't start off simple. Well, they used to start off simple, but now that this idea of deep learning has come about, people believe, or they kind of feel that they should start with a complex model. Remember, a complex model in terms of a neural network are these huge neural networks that learn from data that have many different hidden layers. So overfitting may happen when you have a complex model where it learns every minute detail and the noise that is included in the training data. So you may say, what is noise? Noise is Of course, if it's image related, we think about pixels that are not representative of the particular class that you're trying to learn. In this particular example, from housing information, it could be outliers. It could be actual numbers within the data set that were fat fingered, where somebody was typing it in, but that noise information was either too low, too high, whatever, and it's not representative of a real life situation. And so when your model learns this noise and this detailed information, what can happen is this idea of overfitting, and performance of the model on new data that the model has never seen before is low due to this overfitting. Regularization, as mentioned in the section, is one particular technique, and this technique is borrowed from regression to minimize the effects of overfitting. And we'll show exactly what that is. The next slide. Okay, so regularization involves summing all connection coefficients squared or an absolute value to penalize the model with too many coefficients with high values. So this, as mentioned, was borrowed from regression. There are many different examples of regularization. So I think in the example that was provided yesterday, there is this example, but then there is level 1, L2 and L1 regularization. For purposes of time and just to give us more time, I'm only going to go through one particular technique, and I think this is the technique talked about in that section, but then there's also least squares, which also was another technique that is borrowed from regression. So let's say in this example, we have Y, which represents the learned relation, and beta represents the coefficient estimates for different variables or predictors. So remember that our neural network is nothing but a linear combination, right? Where we first started out, it's a linear combination, and it has weights that are assigned to our input values. So when we think of this, we can say that we can try and minimize the weights that are in front of our values so that we can make sure that our model is not learning this noisy information and that the weights are low for things that it shouldn't learn. So I'll answer questions about this, but I did want to show an example. Any questions about this slide? Okay, so as mentioned, there's another technique as well that we're going to get into. But regularization, people believe that just because you've done regularization, that usually the coefficients that are in front of, or the weights that are assigned to your different neurons within the neural network, that you're not going to have any problems of overfitting. That is not true. And the reason being is because what ends up happening, regularization will create a simpler model by minimizing the weights of features in the model. This is good, and sometimes this is bad. The reason being is because it's doing it randomly, the models that use regularization techniques, they start to lose influence of the important properties with weights close to zero. So bias in the model is introduced, and then you have this technique of underfitting. So it's good and bad, right? So there are other ways so that the neural networks that are actually learned can actually be more simpler. And another technique is, before I move on to that, questions about this slide? Okay. Okay, so there are 3 different techniques. And for the most part, what you'll see, people will try regularization, people will try early stopping, people will try dropout. The technique that a lot of machine learning researchers and people probably say is the best technique is 2, which is early stopping. And we'll talk about what that is. So we've already talked about regularization. Regularization tries to minimize the weights that are in front of the neurons that are within our very complex neural network. Early stopping happens when we want to choose the model that performs the best on the validation model. So a lot of different machine learning APIs and libraries provide functionality to where you can plot both the training and also the validation loss. So remember we talked about what softmax loss was, right? And with early stopping, what you do in this technique, you follow along as your model is learning. So you plot the function of training loss and the dev loss. So in particular, dev loss is, in this instance, is the softmax loss that occurs when using the validation loss. And you stop where the dev loss is the lowest for the validation. So in this particular graph, we have where the training loss, you want it to be as low as possible. But what ends up happening in overfitting, the validation loss actually begins to mimic a U or something like a L. In this example, you want to make sure that you pick the actual, that you stop early, you stop from the learning process, and you pick where that validation loss is the lowest. A lot of different programmers, researchers, machine learning researchers utilize this technique because you are most concerned about picking a model that performs the best on data that it has not seen before, or that it has not representative of the training set that it's learned from. So this is a technique that I would probably say most people utilize when they're setting up their models. Now, there's nothing wrong with doing some of the other techniques, which I'll talk about. Dropout. So there also is another technique called dropout. Dropout is when you have these huge neural networks. So for purposes of actually saving the space that is on this slide, we only have 2 hidden layers. So this is illustrative, right? Technically, this is not a model that it could suffer from overfitting if you trained it forever, because any model can suffer from overfitting. However, in cases where you have huge models that are able to learn the intricacies and noise of the training data, you would want to randomly drop some of the neurons. Remember, the neurons in this example are represented as the O's. You would randomly drop some of the neurons to be excluded from the neural network using a fixed probability as a way to pick the neurons. So this is only for illustrative purposes. So let's say this one is randomly picked. What would end up happening is you would drop that neuron, and so the weights for that neuron wouldn't propagate to the other layers. So when we think about dropout, there is a paper that talks about this more in depth, but usually randomly dropping some of the neurons are only used in more sophisticated, huge, deep learning neural networks. It's not really employed in a neural network that is gonna only have 2 hidden layers. Okay. I wanted to make sure before we go on to everything else, what we're gonna do today, that everything that I covered in that what we learned from the takeaways from part 1 was that I addressed any questions that come about of overfitting, regularization, dropout, stopping early, whatever you may have, any question.
So, Dr. Emily, I think if I don't ask a question, everybody's going to keep quiet. So if you don't mind, I'm good.
Oh,
Yeah,
okay,
so thanks
it's
for
a
addressing.
Friday.
Yes, yes. thanks for addressing the concerns. So one question I have is, with the dropout, is a dropout done randomly and by the algorithm? Let's say if you use the Keras infrastructure, you indicate that you need two neurons dropped out. So then it's going to take care of that, right? Or do you specifically specify which of the neurons you want to drop out? In which case, you in your example, you indicated in the hidden layer 2 that you want neuron 2 and 4 to be dropped out. Does the user have that option, or is it done at random for the user?
Yeah, so it's just software that someone built. So the fixed probability threshold is let's say you set the threshold to be 0.75, and what would end up happening is if a neuron, the weight that is computed for it, for that particular neuron is at or below that sort of threshold, it would randomly pick it to drop it out. And so then that particular neuron we wouldn't use the activation function to propagate to the next level. And that's important because remember, with back propagation and forward propagation, the activation functions are calculated either at the end or at the beginning. So in this example, let's say it's an example of back propagation where you start at the lowest or the final hidden layer. So in this example, hidden layer 2. So in this example with dropout, if there is this fixed probability where you have a threshold, you would be able to say that the activation function within that neuron is not utilized. So therefore, that neurons and its weights do not overpower the others. But yes, the programmer or you yourself wouldn't have to say, I'm going to randomly pick this, this, and this. For the most part, like there are some programs, Skylearn, I believe it has it. TensorFlow may have it as well, but it would be like an option that you could enable when you actually set up the model.
Thank you.
Mm-hmm. Okay, so what today was gonna be more towards answering questions and more practice. So what I wanted to do today was actually go through more practice. And the actual example that we had saw yesterday was an example to show you a neural network that had more than 2 layers, right? It had 30 layers. So it was the definition of deep learning, right? So the examples that you guys are going to go through today will be examples that are more non-deep learning. Okay.
Dr. Washington,
Mm-hmm.
can you, actually I went through this, your studies class thing. So can you again, little bit explain about the model accuracy, the graph thing, how do you get the coding, visualization, loss and accuracy thing, and also the epoch, so it's too many, how we can read this thing, like a HIST model thing.
Oh, you mean
Like it's a how can I know that which is yeah, because like Keras layers, sequential thing, then when you did it sigmoid function, then you HIST model thing, but it's accuracy, and they have a lot of number there. So how can we know that this is a good model or not?
which one are you looking at? You're looking at the one from yesterday?
Yes. Or you can go.
Okay, so I think this is the first model.
This one, yeah, this one.
Yeah. Okay, so the thing that's most important in this is, so it shows you the epoch, it shows you the value loss, it shows you the value accuracy. And then what's usually calculated at the end is this overall accuracy score. So
what about the value loss? So accuracy is called 89, right? So what about the value loss? Minimum or maximum? So value loss, that's the last one, the 0.66. That is the, we consider the last one as the best, right? 0.26. Okay, accuracy. Okay, 89. Okay.
yeah, so
Okay.
in this particular example, so remember that it is doing gradient descent for each individual epoch, right? So because it does that, it also calculates the accuracy for that particular step. So remember that you want to make sure, of course, that you have high accuracy and that you're not overfitting. So you're running it in this example for 100 epochs, and the highest one that it was able to get was 0.8950. And it tells you where that occurs at. It occurs actually at loss 0.2629 and then accuracy 0.8950.
Yeah.
So of the ones within here, it didn't occur at the end. It occurred higher, right? Yeah. So you would say, okay, let me pick that model, that example of the model of when that actually occurred. And you would use that once again to actually run on new data.
Okay.
So and I know you also said plotting as well.
Yeah.
So for the most part, what usually some of the particular libraries, they give you plotting, ability within them. In this particular example, all they did was plot the individual value loss and value accuracy for each individual, the training, and then also the validation set. So they plotted them together. And so if they had run this forever, or for, let's say, more than 100, what would have ended up happening would be the actual, what is that, orange line would have done like a L or a U, because it would have went back up, right? And so that's overfitting, and you don't want that to happen. Other questions?
Okay,
No?
I think.
Okay. So what we were going to do today, underneath your Codio folder was more, what says advanced, but it's not really advanced. It's starting from scratch, right? So it's starting from nothing. So in this example, you're creating a study to actually predict using hours sleeping, and hours studying. So all you're doing is setting up an X and a Y, which is an array of hours sleeping and then hours studying. So you're going to utilize that data to create a very simple neural network that only has, I think, 3 hidden layers. Yeah, it only has 3 hidden layers and then 1 output layer. So the 2 individual variables that go into it are the sleeping and hour studying. So in this example, you're trying to predict the score on the test by using hour sleeping and hour studying. And basically, what I wanted to do was go step by step, at least through this example, to show how to build your own. Of course, you can build your own without utilizing a library that that is already out there. TensorFlow and all of these other things already exist. However, if you like to code, you can also build your own. So in this example, going step by step, we set up an array, and these numbers are not randomly picked. They were entered. If you feel like changing them, you totally can. Remember that X is the hour sleeping. And then, this is the hour sleeping, and then this is hour studying. And Y is what you're trying to predict on the test, the score on the test. So you have Y here, which is 75, 82, and 93. And 75, 82, and 93 are the score on the test. So you're just building an initial array that contains those values. So this is very simple. It almost sort of mimics the example I previously gave. Any questions before move on from that? Okay. All right. So basically, when you run these cells, all it's doing is populating these arrays. And part 1 moves on. All this did was populate the arrays for the output of the score on test and hours sleeping and hours studying. The part where it gets a little bit more interesting is you look at the shape of each individual one. But the part where it gets more interesting is in part 2, where you are creating a class called neural network. And in this class, you have set up this neural network to be an input layer of having 2. That means 2 neurons, right? And those two neurons are hour sleeping and hour studying, I think, yeah. And then so you would have hidden layer size, and it's set to 3. That means that you have 3 different hidden layers, and then 1 output layer, which is you're trying to predict the score on a test.
Can you say again? So is a neuron 2, 3? How do you get the setup? Is it based on input? The neuron is the size 2, 3.
Yeah.
1 is okay. Output 1, okay.
So
3.
3 is the amount of hidden layers. Remember, 2 is you have the 2 different variables that you set up in X and Y. X and Y were,
Okay.
I'm sorry, part 1. Part 1 were hour sleeping and hour studying. So if I drew it, I don't know if you can't see that. It doesn't matter. Anyway, it's hour sleeping would be 1 neuron and hour studying would be the other. And then I would have my 3 different hidden layers and then 1 output. But they would be fed into, that you cannot see. But basically, the only difference is in this example, it is a simple neural network. It's simple. It's not an example of deep learning because it only has 3 different hidden layers.
Dr. Washington, quick question.
Mm-hmm.
So how do we decide the hidden layers? I think that's where I'm getting confused. I understand like the different predictors, but the hidden layers I'm a little bit unclear about.
So that's a really good example of something I was gonna touch on at the end. Let me show you this really quickly. Hidden layers are not something that you like. Using a deep learning neural network is not something that you have to do, right? Simple problems can be solved with simple neural networks. And your hidden layers that you provide, you can start it out with 2, you can provide 3, you can, I've never seen 1 before. I think it doesn't do that. But the hidden layers are just stuff that you are experimenting with. If you have a larger, more sophisticated problem like image recognition, biometrics, though the hidden layers that you give within that particular instance probably does need to be a deep learning. It should be about 30 to start out with, and some can go all the way up to hundreds and thousands.
Okay.
So,
All right. Thank you.
and then also, deep learning is like a buzzword that, you know, I didn't necessarily for this module have to teach. However, it would not benefit you to not understand it. So you can definitely solve simple problems with simple architectures where you only have 3 different hidden layers, or maybe even 2, like in this example, and really get good results. Another thing to mention is the type of data that you have. So there was, I think, controversy as it relates to like these huge models that BERT, which is Google, are building. And you can actually solve problems with support vector machines of only having 500 examples of your input data. So just because you're learning about neural networks, it's like a thing that people are utilizing now, but don't feel like you only have to learn about neural networks.
Dr. Washington, Rocco wants to ask a question, but according to him, he cannot unmute his microphone. So if you can see the chat area, if you cannot, I can read it to you.
Okay. It says, do we introduce like an error when we use the dropout? I mean, we get an approximation of our result. Yes. So yes, dropout introduces bias as well. It's the same way that adding regularization introduces bias and underfitting. So with every different method, there's a trade-off to what you're getting. So that's why a lot of programmers use early stopping, because you haven't really changed any of the neurons. It is truly, you know, a representative of your input data, and then you're also testing on your validation data. But it allows you not to introduce that bias that could occur in the model. So a lot of people utilize early stopping. Did that answer your question, Mr. Giordano? Okay. So with anything, there's a trade-off. Practice, practice, practice. Okay, going back to Codio. Okay, so in this example, the question was why the neurons of only 2. Sleeping and hour studying are the 2 neurons that we are using. So we are going to use a 3 hidden layer neural network to transform this input into a prediction of the score on the test. Questions about that?
Dr. Gloria, so looking at this, I think I'm also getting confused as much as the student is. So in this example, which is the second notebook, So the first, I think, is the first notebook. That's the one. No, it's the second. So the first notebook is just reading about this, but the second notebook defines your architecture. So I think the architecture is where Azad it's also getting a little confusing. So in there it says that the self-input layer size equal to. Does that denote the number of neurons in the input? So the architecture actually defines one input. Okay, so we have one input, one hidden layer with 3 nodes and 1 output. Is that the architecture that we are working with as far as part 2 of the IPython notebook goes? Just to put ourselves into context, so that we just don't run the program as is, and trying to get it from your end.
No, I understand. 1 second, I'll draw it for you.
Okay, yeah. So.
And I'll turn off my I can't draw, so don't hold it against me.
So if you have access to the chat, maybe I have a link in there. So if you see whether it's yes or no, then it will save you the drawing.
You want me to click on this?
Please. Yes, please. Let's see if that is what.
It was invalid. I don't.
Yeah. Okay.
Let me show you what I drew. Let me go back. How do I turn off the? For now, stop sharing. And how do I? Oh, there it is. Change virtual background. None. Okay. Okay. So do not judge me, right? Okay. So this is our sleeping. This is our study. These are the 3 hidden layers. This is the score.
I'm sorry, Dr. Washington, we can't see because of your background. Your background has a, if you can remove your background image, we can see it.
Oh, can you see it now?
Yes.
Okay. I can't draw. Our sleeping, our studying. 3 hidden layers, the output. So in that example, the 2 different things, our study, our sleeping, you need an individual node or individual neuron for each individual one. Remember that with neural networks, you're transforming this input into the output. So that's why you need 2 neurons to represent those 2 different things.
So output will be depend on the hidden layers, like so if you have a 1 hidden layer, so it may be lower prediction, like that.
No, so the question was, does the output depend on the hidden layers? Was that the question? And the use of the number of hidden layers? Well, yes and no. So yes, so in this example, it's a very simple neural network, right? So 3 was chosen as 3 different hidden layers. You could have started out with 2, you could have started out with 4, but it was truly chosen 3 to start out with, just to see what you would get with prediction.
Okay.
And I think the confusion is, if you have 2 different input, like in this example, hours sleep and hours here, does it have to be greater? I think you're probably saying, well, if I only have 2, do I have to have some minimal layer of neural network or neural network hidden layers? No, there's no hard and fast rule to that. However, most people start out with at least 2, and then they'll move along to see the prediction, accuracy prediction. So in this example, the reason why 3 was chosen, it was just chosen at random. Did that answer the question?
Yes, thank you.
Mm-hmm. Okay, going back. Okay. So going back to this, in this example, you are creating a class called neural network. That is a non-deep learning neural network where it has 3 different hidden layers and then 1 output layer. We are using forward propagation, where the actual activation values and weights are propagated at the end. And we are using a sigmoid function that squishes everything between 0 and 1. Questions about this now?
It's 0, 1, 1. It's minus 6 to 6. The sigmoid it looks like a minus 6 to 6
With
on the graph.
Oh.
It's not 0, 0, 1. Okay, let's see that except part 2. Yeah. So
This
okay,
sigmoid,
0, 1.
so
Yeah, I got it.
Yeah, okay. It hasn't been called yet, but okay. Anyway, so as you're setting up your class, the class is here, right? So these are your functions that you're gonna call later in this next section. So now we set up a variable called NN where we instantiate our class. And then from there, we're just arranging using np.arrange. And this is just plotting just to show us what we set up. And then we call the sigmoid function with 1 in it. Just to show what it would do. And we're calling the sigmoid function on np.array, which actually transforms this array to show what it would do. And then there's this function that actually gives us random variables. So in this example, the random variables for the most part will be utilized for initially setting up your hyperparameters for your hidden layers. Questions about that?
So the difference between this one and the second one?
Yes. So then you're setting up another class called neural network that takes in an object. The difference between the other one was that it didn't accept any, well, it did accept input, but this one has more different information related with it, where it basically is the same structure, but the weights are different and the weights are set up. And then also forward propagation is actually populated. In the previous example, forward propagation it didn't do anything. Okay. So those weights where it says self dot weight 1, self dot weight 2. So remember yesterday we had said for every input variable, initial weights are created. So these initial weights are created for our sleeping and our studying, right? So those initial weights are created. And because we're using forward propagation, that means that we're propagating the weights to every individual hidden layer as it goes throughout the actual neural network. And when it gets to that final hidden layer, it has all of those weights that are propagated. Questions about that? One thing to note, yes, there was a question. Yes, okay.
So
One thing to note. Go ahead.
So in first one is a 0.73, right? The predictive probability 0.73. What is it? That one? This line 19, 7.73, right? This and the line is outputs 19.73. Output
Yeah, so
19, like a sigma.
are you running it and seeing 0.73 being output, or you're looking at what I have?
What you have? I didn't run it. Yeah.
Oh, okay. Okay. So then also, all we're doing is outputting what's happening, creating an instantiation of what we just did of that neural network by updating in now, and then actually with y hat, we're getting the values that have been propagated into the neural network, and we're just printing out that information. So the initial weights for y hat are 5.6 or 0.56, 0.44, 0.541.
I have a question. Going back to the random variables in 22, for the self.w1, is that the weight? When you said weight, because I didn't, understand clearly where you were talking. So you were saying self.w1, is that the weight one?
Yeah.
That's within the four propagations?
So, yeah. So remember that each individual input variable, which is our sleeping and our studying, initially the weights are going to propagate to the end. So W1 is weight 1, W2 is weight 2. And because there are 2 neurons that are initially in our network, you need the weights for each one.
Okay. Thank you.
And before that one, you have a line. It's a 213. Why is it's just you set up the number, or it's maybe 1, 2, 3?
It's the exact same thing. They just wrote it in a different order. So the input, yeah, all they did was in this example put output layer size before hidden layer size, but it's the actual same architecture of that neural network. 2 individual input layers and then 3 hidden layers, 1 output layer.
Output layer.
Okay. So one thing to note with forward propagation is that I didn't go over the math of what it's doing, right? But in order to propagate everything to the next layer, you're computing the dot product, and that dot product is then propagated to the next layer. All this is doing is calculating that so that you're able to propagate it to the next layer and the next layer and the next layer for each individual neuron within a layer. Questions? Okay. So that is the end of part 2 or whatever. Before I move on to this, remember this is a simple neural network and very simple for the most part. Basically, this is doing the exact same thing, but I think what they're doing here is everything that was in part 2 was imported as for this part. So what they're going to do now is, remember you have the weights that are propagated, so all it is plotting that information so you can see it. So remember that Y is something that we are trying to have a prediction for, and Y hat was the actual scores that, not scores, weights that have been propagated. So we compare the estimate Y hat to an actual score. You know, all this is comparing them together. So you can see what it is going on.
So I had is just like a regression, right? It's not a classification, right?
No, Y hat was calling, oops, yeah, Y hat was calling, there it is. Y hat in this example was calling forward propagation of the entire neural network. And you get these numbers. Okay, and so with here, so you're saying in a range from 1 to 1,000, you're gonna get weights to try for that individual neuron, and you're gonna utilize the forward propagation to update those weights. And then you're plotting it. Basically, I want to get to where it gets interesting. So once you get to part 4, you'll be able to see how well your model is doing with test values, and you're plotting that information. And then I don't envision that you'll probably get through all of the parts today, but I do wanted to make sure that you understand so that you can run it on your own, like when you're at home. Well, you are at home, but like run it on your own. And when you get to part 7, some of you'll be able to check the gradient descent, which is what we had talked about basically yesterday, and talked about a little bit today as well. But you'll be able to see that as well and plot how you plot this information. So I will say, normally when you are performing or utilizing neural networks, you're not going to build it from scratch yourself, right? You're going to utilize like a TensorFlow, or you're going to utilize what we used yesterday. You're not going to build it from scratch. So this is truly an example to show you that you can build it from scratch, and you can build your own from scratch if you wanted to do that, if that interests you. But as you're trying this out on your own, this is kind of an involved thing because there's 7 different parts. Try for yourself to at least try and do the part up to gradient descent if you can. I think you can skip some of them. But since it uses this part from part 6 to import, it's just saying that it truly believes that you're going to go from 1 to 2 to 3 to 4 to 5 to 6 to 7. So it's dependent upon each other.
Dr. Washington, just a quick question. I've been trying to transition from part 1 to part 2, but it seems like I need to replace the star with something for the import. I don't know what I'm importing from part 1.
What error are you getting?
Let me try it one more time. Saying no module in part 1.
I don't think it knows where it is. What you could do is copy this, except for put all of like these at the top of that. Because you only need this part where you set up the X and the Y for that. You could put it at the top of that and then comment out this line to where you won't need it.
Okay. Thank you.
Mm-hmm. But should you get that error, it looks like it's not seeing that it is under the same directory, but it is.
Mm-hmm. So if we were to do this in Jupyter Notebook instead of Codio, could we use like part 1, part 2, and then run it like it is?
Yeah, I mean, it worked for me
Okay.
without having to do that. I'm unsure why it's doing that now.
Mm-hmm.
Does our William, do you have any suggestions of why
No,
it's not in?
it had a problem. I know when I do the local drive, it's had a problem with the something with the download. But when in the morning I try to throw this Codio, I don't have a problem.
So can you see the file? Are you referring to the CSV file? I mean, what is the specific of your problem?
So when I run
we
the
can
code,
we can work with, yeah, we can do it offline, but
yeah,
I tried it. It didn't give me any error.
Okay, let me try one more time. So I ran the code in part 1, and I went to the next tab to go to part 2, but it's not finding part 1.
Yeah.
Let me try to
because your
rerun part 1.
environment. Yeah, because it thinks your environment you are in 2 different environments. So just as Dr. Gloria mentioned, you can just copy and bring it over. Bring the segment over. Just create a new cell and paste it over. It should have worked though, because it's the same environment.
Yeah, I thought it should work since I was in Codio,
Yeah.
but I don't know.
Yeah. Because it works in my Jupyter, but let me try it.
Yeah.
Okay.
And then sometimes I've found when I lost connection and what I ran in part 1, it didn't realize that I lost connection. So I had to rerun everything in part 1 and then run part 2, this prompt at part 2 again, and then it would know.
Okay.
If you don't envision you lost connection, it could be something else. Yeah.
Okay. Thank you.
Mm-hmm.
So Ken, yeah, I see that. So part 1 and part 2, they don't seem to share the same environment. So when I run part 1, let's say I took the X and the Y, which is like line 6. I run line 6, and I went to part 2, inserted a cell, and tried to print the value of Y. It gave me an error. So that might be the problem. In which case, just copy the code.
Yeah.
Yeah. So the environments are not shared. Yeah. Okay.
And hopefully you won't encounter that going forward because some of them get a little bit long. But as we are, basically step into the code, I really wanted to give you guys time to work on this, ask questions about what you're seeing, what you're not seeing, anything else that you may have that doesn't make sense or want me to expound upon more. There was another tutorial I'll put in the link as well that I found that starts off with image classification. I only get to this if you this is something you really want to, start to look at. But I thought it was interesting. It wasn't that one. Here it is. And I'll put this link in the chat. So what I'll do, since we're just quiet, since we're all quiet, I'll just finish up the presentation as you're working. Listen to me if you want to. um, Yeah. So as you're working, I'm just wrapping up everything in a nutshell that you have learned throughout these 2 days. So neural networks can be really complex or they can be really simple. Sometimes there are different architectures that you guys may want to start to look at, like if they're, I don't know if we have this module support vector machines or hidden Markov models. One thing to note as well, the data that you have, like if you, neural networks, specifically deep learning neural networks, assumes that you have lots of data to train from. And a lot of times you're not going to have lots of data. Support vector machines find themselves to work well. And when I say work well, with at least 500 examples of things that you may have for the type of problems that you want to predict. So those have proven well. Support vector machines have proven well, like natural language processing. They've been used with automatic code switching, which is something that my student is doing, and then automatic translation of languages from one to the other, where you might not have a huge data set where you have a lot of different examples. So something to think about. And for simpler problems, keep it simple to avoid overfitting. Also keep it simple just in general for yourself and to be able to understand what you're actually using. A lot of times we can utilize these systems out there, and of course, we want to start with the strongest model, or we believe is the strongest model, which is a deep learning approach, which has more than 5, hidden layers. But if your problem is simple, keep it simple. Deep learning assumes that there are hundreds, sometimes thousands of hidden layers, and it's not always best for simpler problems. Deep learning using neural networks are great for sophisticated computer vision problems. And some of the things that we think about to avoid overfitting, which is finding, overfitting and finding the best model, is what you want to do is specify some hyperparameters. These hyperparameters, like we think of in the case of what you're working on now, which is hours sleeping and hours studying. Those are the specific input that you want to transform to be this output, which is usually a classification. So you want to train on the training data set. The training data set, remember, you want to train on as much data as you have possible. There are various techniques to figure out the difference between the training, the validation, and the test set. But you can specify specifically with like scikit-learn, where it's 30% of the original data set can be your test set. And then within that 30%, they actually carve out another subsegment to be the validation set, or you can do an 80-20 rule, or you can say, I want to set up my own way of doing it myself, where you randomly pick rows from a comma separated file that you actually want to include, rows or columns that you actually want to include for your training set. So you basically train on this data that you have utilized. You record the validation loss. The validation loss is truly what you want to look at when you are picking the model that is best for your problem. The reason being is the validation set includes data that it has never seen before. It includes data that should challenge the model. So if it performs well in the validation set, then it's something that you actually want to record and use that model. So sometimes you will need to repeat these steps many different times to get the highest number possible of accuracy of the correct predictions for your particular problem. So in this example that we have, you're starting out with a hidden layer of 3. The ratio between the input layer and the hidden layer, it's not set in stone. You can start out with a neural network that has 3. You can start out with a neural network that has 5. It just depends on if you feel like you're over complicating something for a simple problem. Then you want to pick the model with the lowest validation loss as your best model, as mentioned, and then you want to run the chosen model on a separate test set. So you can have many different test sets that you get, as mentioned. You can have someone, a researcher close to you, who provides you another set that is indicative of what you may see. But since the model hasn't seen it before, you would run it on something new and see how well it performs. And usually this isn't a step where you're just automatically going to do this once. You're going to do this several times. It's not something that, is set in stone. It's just all based on your particular problem and the solution that you want to be the best solution, which is a model that actually has high accuracy, but then in validation, it has a low validation loss. As mentioned in the appendix, I won't go through those, but I just put some resources for you guys to look at if you also want more information about like those cheat sheets and stuff like that that's out there that actually comes into play for doing data prep. And data prep is very important because garbage in means garbage out. Cool. Okay.
I'm sorry, did you say you had a link for data prep? I didn't hear that last part.
Yes, I put them at the end in the appendix. So like there's data filtering, data cleaning, and it links to the DataQuest site. So you can go to those when you have time.
Okay, thank you.
Mhm.
Dr. Gloria, just a quick question. I think we have a link for your first presentation, but for this presentation, I don't think we do. At least I don't have the link. Is it something that's accessible?
I put it in the slides too. I put it here, and then I downloaded the PDF of it and put it here.
Okay, thank you. Yeah, thank you.
Mhm.
I'm having that problem also with the part 2 with the error messages. Is there a way that that can be corrected?
Let's
Because
see.
it's not actually carrying over from the previous part 1, the import.
Yeah. One second. Are you on part 2?
Yes, I'm on part 2. So what I tried to do, because it's not doing anything, I tried to actually get the different code to put into part 1 at the bottom. It still did not do anything. It still came out with an error.
So
maybe I don't know if Nana's on the line, but anyway, maybe you can help with that issue. But I'm in Codio, so it's just there what I'm looking at, but it's just not carrying over.
So what do you have? What do you see on your screen next to the Python icon, which is a blue and the orange? Does it say trusted or non-trusted?
Okay, so in part 2, what I'm saying, it's a percentage sign, PyLab inline from part 1 import, and it's like a asterisk.
Asterisk, yeah. So that should work. Now, I think your problem is that your Anaconda environment is not realizing. So look at the very top. The top, you see something like Jupyter part 2. When you go to the very far right, what do you see there? Do you see trusted and Python 3 or untrusted?
I see. I made it trusted. I actually made it trusted.
Okay.
Yeah, because at first it said not trusted, so I made it trusted. So it's now saying Python 3 also.
Yeah.
But yeah, I tried that as well, just to make sure.
Yeah, you should see something like populating the interactive namespace from NumPy and Matplotlib. That should be the output. If you see something different, then maybe Dr. Gloria, no, because you are not on coding. Is it possible to have a share her screen if that would disrupt the class?
You want to share the screen? Okay, one moment. I have 2 monitors. Hold on for a moment, please.
Take your time.
Okay, so I clicked on share.
Even I did the trusted, it's part 2 still is showing error. It's the same like Helena mentioned.
Okay. Do you see my screen now? Share. Okay, so you see where it says trusted and over here Python 3.
Okay. Let's see if I can find something else.
Can you please click in part1.ipython notebook? So bring part 1 in view. Okay, cool. So now it should recognize that. Now, just for the sake of it, just run the same thing in part 1. So just hit Control and I'll just hit the run. Yeah. So now, now it should work, and that's the same thing you're doing in part 2. So if you go to, I think because you didn't have it in view. So now go to part 2 and try that, and let's see.
Okay, because I tried that before, so maybe it'll run now. I don't know.
Yeah, let's try
Okay.
it. Or I'll do control
Yeah.
enter. Do control enter in there.
Control enter. Okay.
Okay, we'll take care of the joint TA session, which we don't want to take of that
Okay.
progress because this is a TA. It works for me and it works for others. So yeah, sorry,
All right.
Dr.
So
Glenn. Yeah, sorry for that.
okay, we'll take care of it.
Is that a Codio environment issue?
Yes,
William.
it
Oh,
works
okay.
for me though. Yeah, it works for me. So we'll take care of her during the TA session so that we don't take
Oh,
all of
okay.
it.
Okay.
Okay, so Dr. Gra, I think I figured it out. Uh, so I think the import is actually looking for a .py file. So then it complains. So let me show what I did here, if you don't mind, please. I don't mean to take over your class.
Oh, no, that's fine.
Okay, unless you're ready to. Yeah. So I'm sure others are struggling. So let me share this quickly. So please sharing this quickly, and then for the rest, we're going to do this during the TA session. So don't worry. Okay. So this is what is happening. In the mod 2, I think the way I did it is I cheated a little bit. I had a part 1.py in my ANN advanced part practice. So that's why it worked for me. And so what I did was so to get yours to work, all you have to do is to save this part 1.py, save it as .ipython notebook, export it as a PY file. Okay, it's going to go to your download. Okay, so if you go to your downloads, you see that the file will be sitting there. And I think there's a problem with Codio. So don't worry if you're having a hard time. But if you go to your downloads, you will then be able to see that file, and then you bring it over. Okay, so just bring it over. So if I go to my environment and I go to my downloads, if I can find my downloads should be somewhere in here. I have a quick link for that, but okay. So if you do that, you're going to see, you're going to have access to a .py file in your downloads. Okay, so like this guy, just rename. I've done it twice. That's why I have it shown. But if I make it a .py file, okay, .py, okay, then you can just pick that py file. Okay, it's telling me, yeah, so pick this file and put it back to your Codio. Okay, so let me go to my Codio, come back here, and then pick this py file and drop it in this environment. Okay, so you see it's there. So now if you go here, okay, so we're going to try what we did like in part 2. I'm going to just try and open a cell and move this cell up, okay, and open one more cell. Then if I say from, okay, so what the Gloria did is part 1, part 2 uses part 1, and part 3 uses part 2. It's correlated. So you're saying that, hey, you know what, I'm in part 2, but I want to call part 1 in. The way to know if it works, once you hit PART, you hit a tab, and you see all these files. Those are the files it can see. So you would have to pick one. Now, if you pick the one with the PY, then you don't have to add a PY. Python knows it as Python knows to add a PY. If you don't save it as a PY, then you have to indicate that you are loading the IPYNB file. So if I do this, it's going to work. So you see it works. If I do anything else, let's say 1.4, it's going to complain. It's going to say, I can't find it. And that's what the problem you guys are having. So you have to, now let's try and see if it will be able to pick the IPYNB file. So you hit a tab, and you see it cannot see the IPYNB file. Okay, let's say part 1, this one. Let's try that. And that won't work because Python needs a .py file. So you have to use a .py. You have to save it as a .py file. Then you'll be able to load it. The same thing here. You see what I did? I saved it as William part 1 William py. So I can ask it to load it. And the trick is that if you hit a tab and you don't see the file, then you're going to get an error. Okay, so this will work. That makes it work. Okay, so yeah, so back to Dr. Gloria. We'll work on this. Please don't worry too much. Just make sure, ask Dr. Gloria the technical questions. And these ones, if you cannot run it, we'll work on it. The alternative, as Dr. Gloria said, is to go to part 1, copy the data, put it in part 2, and then you'll be able to keep going. Okay, because all you need is the data. So if I bring the data here, then I can just keep going. Okay, I can just keep going and shift enter and shift enter. Okay, and then X dot is missing a print. Okay, just try it. If you get an error, just keep note of it, and then we'll come back and do it. But that solved that import. The rest of it, I think we'll worry about it as we go on. There's something here that I can't figure out. Oh, the
So
print.
why,
This is a
Dr.
Python
William, so why is not
Yes.
working? You copy the data in here, and why again is showing error?
Oh no, it's not. It's showing error because the print was a Python 2.7 type print. You see, Python 2.7, you don't put a parenthesis around it. But Python 3, which is what you are running now, forces that print as a function. Okay, so this is a Python 3, so it's enforcing a print. So this will give me an error. But then once I go in, and it tells you here, If you look in the bottom, it said, did you mean to? Yes, so you just go back here and put a parenthesis around it. Just pay attention to the error message, and then I think you'll be fine. Yeah. So if I do this, then it should work. Okay, so I don't want to take more of Gloria's time, so we'll take care of the joint TA session, please.
Thank you.
No problem.
Have a great weekend.
Thank
Oh, no, don't
you.
go. Don't go. I've not dismissed you. Dr. Gloria, I have not dismissed you. Please, don't go. Let me pass you, Dr. Gloria, and then I'll mute. Yeah. Thank you, Dr. Gloria.
I'm just waiting for questions. We're just going through it and I'm waiting for questions, so it's totally fine.
Okay, hi everyone. I think some of you have already left, but we want to thank Dr. Washington for 2 days of very informative and excellent presentation. So for those of you still around, put your cameras on and let's show our appreciation to Dr. Washington. You can wave your hands or whatever. We want to see your faces.
Thank you.
Okay, so hi Martin. Yeah, so next week we have the third of the research presentations, and the topic is ethical data science. You cannot do data science without the ethics. So there will be a 1 hour or 1 to 1.5 hour presentation on data science and ethics. It's Thursday at 11 o'clock, so all of you do your best to attend because that is a very essential element of data science. You don't just want to just go and then analyze the data and think, oh, I'm done. You want to know the ethics of it. So thank you all for coming. I think Dr. Washington is here, or if she wants to hang around a few more minutes, those of you, if you have any questions you want to ask her. Otherwise, have a great rest of the day, and then we'll see you all next week. And don't forget to do the evaluation, and then also the Terra account, if you haven't done so, you want to do so before you will be able to participate in module 7. Okay, thank you all for coming again, and see you next week.
Oh. What is the evaluation survey? I couldn't find it.
Yes, could you put the link in the chat again?
Yeah, so I just posted the evaluation link in the chat area, but I believe it's also in Slack, so you can check that also. And it's not closing today, so I think it will be open for a couple of days, so you can still do it. All right, so I'm out. Thank you again, Gloria, and then talk to you.
Thank you. I'll, I'll stay around for a little bit if you need me.
All right, all right.
Thank you.
Miss Thompson or Dr. Thompson, Helena?
Yes. Hi.
I figured it out. I figured out a much simpler method. I didn't want you to have to go about doing that. Okay, let me show you. That was really bothering me. Okay. So let's say you've ran everything in part 1. So there's a newer version to install. So you utilize the pip install again. So then I can send this to you in the chat. I'll put it in the chat too, just in case. But you run this where it'll import a IPYNB file. So our files are .IPYNB. That's why it wasn't figuring out the difference. I'll put that in the chat so you can copy it. And then once you run that, you do it the same way that you were doing with the PyLab or whatever. You just don't have to use that anymore. It's now import underscore IPYNB, which now allows us to utilize that file. And so you say from part 1, import everything. The asterisk means everything. And I'll copy this too, so you can have it. And then it'll recognize it. And you don't get that error anymore. And it tells you importing Jupyter Lab notebook from part 1.INB, blah, 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 blah.
Sounds beautiful. I use a lot of snipping too, so I just copy the whole screen. So that's fantastic.
Yes, and you'll probably just for all of the parts, just replace that information. Now that you already have it, import IMP, installed, you don't have to install it again. But yeah, just use that instead. And I'll send that to William so when he has it for the people who jumped off. I was trying to find it before they jumped off, but yeah.
Thank you. I'm glad I hung on.
Yes. Well, have a good weekend. And if you have any questions, if you're running through this, I'll be available through email.
Okay, I definitely will do that, email you if I have any other questions. I am an undergraduate alumni from Howard University, and I just finished graduate work at Rutgers for biomedical sciences, and it's informatics. So I basically just finished that in January. So I'm trying to get back into a different career. Yeah, but anyway, I'll definitely email you, let you know how it went after I download, and I'm sure it will go well. Okay. But thank you so much for your assistance. This has been a great course.
Thank you. I hope you learned a little bit, and I tried to be as plain as possible. I hope I helped.
You did, definitely. Thank you so much.
Have a great weekend.
Thank you.
You do the same. Thank you. Bye-bye.